Here's our example for project 4 using the standard candle method. All right, so this is an example. I used a similar galaxy to the actual project 4. Anyhow, let's just say that there's a type 1 supernova. By the way, these are actually called type 1A supernova. So let's say that there's a type 1A supernova that we observe in a spiral galaxy called M100, which is actually kind of close to or it's in the same direction as the Pinwheel Galaxy. Just to let you know, this is not the Pinwheel Galaxy. It's a totally different galaxy. Anyhow, let's say that we observe the maximum flux. Okay, that's really important, that we observe the maximum flux of, this is the amount of power per square meter that we receive in our telescopes, and let's say it's 5.8 times 10 to the minus 16th watts per square meter. All right, so again, we're going to use the method of standard candles to figure out the distance, and we want the distance in megaparsecs. All right, so here, let me scroll down a little bit. So the distance, of course, is let me rewrite this. Okay, so the flux is always equal to the luminosity divided by 4 pi times the distance squared. Okay, that of course is the inverse square law. We rearrange the inverse square law and we solve for the distance. So the distance, right, the distance goes on the other side of the equation and the flux goes where the distance was. But since we're finding the distance, you take the square root of the luminosity. In this case, it's the luminosity of the standard candle divided by 4 pi, and also divided by the flux. All right, and so we're given the flux of 5.8 times 10 to the minus 16th. Right, it's right there. And so we just have to since this is a type 1A supernova, we can now work out the details of what the distance is. Remember, the distance will be in meters, and then we'll use this conversion that one parsec is 1.3 times 10 to the 16th meters. All right, let me get a fresh screen so we can do this. All right, so just got to have a little bit more room. All right, so here we go. So the distance is equal to, and again, remember this is going to come out in meters, so it's going to be let me just rewrite the equation. All right, so it's the luminosity of our standard candle divided by 4 pi divided by the flux. Right? And remember, the flux is just something that is observed in your telescope and measured in your telescope. So the flux, of course, is for a supernova type 1A is 5 million times the luminosity of the sun. So it's 5 times 10 to the 6th times the luminosity of the sun, which of course is a well-known value. We've used this many times. It's 4 times 10 to the 26th watts, right? And that's all under the square root, right? And then we divide by 4 pi. That's supposed to be a pi. And the flux that we received in our telescope was 5.8 times 10 to the minus 16th. And of course that's watts per square meter. Right? And then of course the watts in the numerator and the watts in the denominator cancel, and 1 over meters squared, and of course you're taking the square root, gives us the answer in meters. And so the distance comes out to be, so here's our distance, the answer comes out to be 5.23 times 10 to the 23rd meters. All right, and of course we need to convert that to megaparsecs. All right, so we're just going to convert it to parsecs and then move the decimal place 6 places to the left. All right, so anyhow, here we go. We know that in 1 parsec, 1 PC, there are 3.1 times 10 to the 16th, 10 to the 16th, 10 to the 16th, meters, right? And so, of course, the meters cancel, right? And that will give us an answer in parsecs. And the answer comes out to be, well, I'd already converted it to megaparsecs, but it comes out to be like something like this: 16 million 900,000. You know, then there's, I'm not putting the correct digits here, so you know, it's a 16, and this is of course in parsecs. But then so these are actual digits. I'm just I didn't put them. Anyhow, we're going to move the decimal place 3 places to the left and then 3 more places to the left. And so that tells us that the distance to this particular supernova, which of course is really the distance to the galaxy, right? Because the size of the galaxy is so small compared to the actual distance that we're talking about. It turns out to be, of course, 16.9 megaparsecs. And so, and by the way, if you wanted to convert this to light years, you could easily do that. And so, of course, in 1 parsec, there are, of course, 3.26 light years. Okay, you don't have to convert it to light years. I'm just showing you this. So the parsec part cancels, and so you just multiply 16.9 times 3.26, and so you get approximately 55 million mega light years. All right, so, and that's approximately the distance to M100, right? Which is a is a spiral galaxy. It's actually a spiral galaxy that's seen almost directly down the rotation axis. In other words, the spiral arms are perpendicular to us, to our line of sight. So it's a pretty fantastic looking spiral galaxy. All right, so that is the example, and then of course it asks you to to verify it, since this is so close, right? Or the actual example that we're doing in Project 4 for the Pinwheel Galaxy. The Pinwheel Galaxy will turn out to be close like this, not exactly the same number, but remember we're doing it in megaparsecs. So you'll actually be able to use Fisher-Tully, right? Or the Tully-Fisher method, right? Yeah, use the Tully-Fisher method to verify this, right? This method of standard candles. So, and of course, just look at the last video that I did for Project 3, which of course was the Tully-Fisher method. All right, so that should get you through this project. And then there's of course only one left, which is going to be using Hubble's law.